Hello. So I just finished playing this video game called Minit, and it's a bit like Zelda. And one feature of it is that after you play the game, similar to some other old games, you can play again. But if you go to the screen, you'll see that you can either play the game again like normal, or you can play the second run version, or the second quest version, if you will. And this second quest is a feature of a number of video games. And what is it? It's like you get to play the game all over again, but everything is a little bit askew. It's slightly different from how you normally expect things to be, and it's a little bit harder. And I like this as kind of like a metaphor for how I think about a lot of problems in quantum computing, and especially quantum information and quantum learning theory. It's like a lot of normal problems in classical learning theory or classical information theory, but you get to do them all over again in the quantum version, and they're a little bit different and a little bit harder, but it's like fun. You get to do everything that you used to do in the classical world all over again. So I want to give you an example of this in this talk with the subject of quantum shadow tomography. And quantum shadow tomography is a cool topic, and it's exactly the second quest of a classical topic in learning and information theory called adaptive data analysis. So in order to tell you about this quantum topic, shadow tomography, the first thing I'm going to tell you about is the classical analog, adaptive data analysis. Now let's in fact start with something even simpler, just data analysis, you might call it. So in the data analysis problem, there's an unknown probability distribution, which you can think of like as an unknown die. It has d sides, but you don't know the probabilities of the various faces coming up. So there are unknown p1 through pd, and outcome j occurs with probability p sub j. And you, as the learner, are interested in a certain event. And what is an event? An event is nothing more than a subset of the outcomes 1 through d. So maybe A is the event of all odd outcomes, or, I don't know, prime number outcomes. And you would like to estimate the probability of this event under the probability distribution p. And I'll write that quantity as p of A, up to some tolerance plus or minus epsilon. And we think of it as expensive to get samples from this distribution, so you can pay for n samples, which are like rolls of the die, and then having seen these samples, you have to output your estimate for p of A. So what should you do? Well, actually, this problem is easy, and you should do the obvious thing, and the obvious thing works well. So I've encapsulated that with what one might call the classical polling theorem. It says you set n to be roughly 1 over epsilon squared, maybe more precisely log 1 over delta over epsilon squared. Delta is another parameter, and you roll the die n times and you get a sample S. And for your estimate of the probability of event A, you just output the empirical probability, which is this quantity I wrote S sub S of A, which is the number of samples that were in the event, or the subset A, divided by n. That's the empirical probability. And the classical polling theorem easily tells you that, except with probability at most delta, your estimate will be correct. It'll be within plus or minus epsilon of the true probability of A, except with probability at most delta. And what's nice about this, or a nice feature of it, it has no dependence on d, the number of sides of the die, so it works independently of d. Okay, so that's an easy warm-up, and let's talk about a problem involving some more data analysis. Now let's say that you, the learner, are interested in multiple events, A1 through AM. And m is the number of events, and I'm going to be referring to m a lot in this talk. So m is the number of events, d is the number of outcomes for the dice, or the die. And you want to estimate all of their probabilities, the probability of A1 through AM to plus or minus epsilon, and you want to get them all correct up to this additive epsilon. Again, you can pay for some number of samples n, which you're trying to minimize, and then you have to output all your estimates based on the samples. What should you do here? Well, the most obvious idea also works well here. So what you can do is take, let n be something like log of m over epsilon squared samples, which is a bit more than you had before, and let s be a sample of n rolls. And you should just reuse the samples. You should do the empirical estimate for all of the events A1 through AM, just reusing the samples. So we'll output the empirical estimate for each of these events. And then the classical polling theorem tells you, since you took, it's like you took m to be, it's like you took delta to be like 1 over 20 times m. So for any individual event, a sub t, the probability of you getting an estimate that's wrong, or not within plus or minus epsilon, is smaller than 1 over 20 times m. And so you can use the union bound to say that, except with probability at most 1 over 20, all of your M estimates are correct up to plus or minus epsilon. Great, so that's well and good as well. But now I have to tell you about a version that gets a bit more tricky, which is what is known by adaptive data analysis. So imagine the following situation. You let S be a sample of something like log M over epsilon squared rolls of your die as before. And you decide to estimate P of A1, the probability of a certain event A1, up to plus or minus epsilon using your sample S. Okay, so that will work well. You'll get a good estimate, except with probability something like 1 over M. And then you might say, let me now try to estimate the probability of a different event, A2, up to plus or minus epsilon, and I'll reuse the samples S. And then having gotten that estimate, you might say, let me try to estimate the probability of another event, A3, reusing S, and so forth, up to M events. And you might say to yourself, this looks good. Are we fine? Is this fine? Well, actually, this is not fine. This is exactly the thing known as P hacking, and it's cheating. This does not work. So actually, if you do this, you'll only provably get good estimates up to the first log M or so many of these A's. And after that, all of your estimates may be invalid with high probability. And what's the difficulty? The problem is here you've chosen the events in an adaptive fashion. You didn't fix A1 through AM ahead of time and then estimate all of those. It's possible here that A2 depended, like which event you're considering A2 might have depended on your estimate for A1. And which event A3 you considered might have depended on your estimates for A1 and A2, and so forth. And since these events were not fixed in advance, the previous analysis does not work. In order to make this work, you'd have to argue that the state, or distribution of the samples S, is still close to, I've written here P superscript tensor n, meaning n independent draws from P, even conditioned on having measured your empirical estimate for A1. And in this last sentence, I intentionally used a lot of words from quantum, like state and measured and so forth, because it's going to be an analogous situation is going to occur in the quantum setting. So what can you do to get around this difficulty? One thing you can do, and it's the classical suggestion from statistics, I suppose, textbooks, is to just use fresh rolls of the dice for every new event, A sub t, that you want to estimate. So you can do this, but then if you have M events, your number of samples will scale linearly in M. It'll even be like, I guess, M times log M over epsilon squared. Okay, and that's quite disappointing. It's exponentially worse dependence on M. Another thing you could do is, well, you could say, I'm just going to use the non-adaptive solution that we saw before to estimate the probability of every possible event A. There are only 2 to the d different events. If there's d outcomes, there's 2 to the d different subsets. And if we estimate all of them, then then any adaptive succession of A's that we choose, we'll already have estimated. So you can get the logarithmic dependence there, but now you have 2 to the d events. So here your sample complexity is proportional to d, the number of outcomes, which is also a bummer. Here, actually, what you've done is tantamount to just learning the entire distribution P. And if you want to do that, then it takes the number of samples that's proportional to d. So we have these 2 disappointing outcomes because they each have sort of linear dependence on the parameter m or d, whereas we were getting logarithmic dependence before. So one might ask the following question: can we solve this adaptive data analysis problem where the number of samples n is polynomial in log m, and maybe log d is okay, and still 1 over epsilon? So that's an excellent question. And it turns out that the answer is yes. This was established only somewhat recently. And how does this go? Well, what was the difficulty that was being faced before? It was that you'd have to argue that sort of the state of or distribution of the samples you had is still close to being n independent draws from P, but even conditioned on your estimate for, let's say, the first event, A1. So the idea was used to solve this problem originally came from the field of differential privacy, and this idea was to use a different estimator for the probability of A1 other than just like the obvious one, the empirical probability. So one should take the empirical probability and, as we'll see, like intentionally put a little bit of noise onto it. So that makes your estimate maybe a bit worse, but it has the feature that given the result, the distribution of your samples S is much closer to being the original distribution of n independent draws from P. So let's check what's been done, sort of what are the records for this problem of adaptive data analysis. And I'll tell you 3 results that are known about it that came out, well, I suppose over 5 years ago. So the group of researchers who originally introduced the problem were Dwork, Feldman, Hart, Patasi, Reingold, and Roth. And they showed that you can solve this adaptive data analysis problem with a number of samples that depends polynomially on log m, the number of events, log d, the number of outcomes of the die, and epsilon, the accuracy. And they got log m to the 1.5, log d to the 0.5, divided by epsilon to the 3.5. And I'm ignoring maybe polylog log factors in all of this. In the same paper, the same group of researchers had a different solution, which got a different number of samples. And that was log m to the power of 1, log d to the power of 1, divided by epsilon to the power of 4. And you'll notice here that I put this into second place, and this other result into third place, even though they're actually incomparable. So some of the exponents are bigger and some of the exponents are smaller. And the reason I ordered it this way is that I believe, at least for my interest, that m is the most important parameter. And then epsilon is the second most important parameter, and then d is the third most important parameter, at least for my purposes. And I'll explain why at the end of this talk. But for me, the most important parameter is m, and therefore, as long as you're polylog d and polynomial on epsilon, then I prefer this dependence that's log m to the power of 1 rather than log m to the power of 1.5. So those results were from the original paper, but then the top result is from a subsequent paper by Basli, Nissim, Smith, Steinke, Stemmer, and Ullman. And they achieved log m to the power of 1, which is great. This is optimal because even for the non-adaptive version, you need log m over epsilon samples. And log d to the power of 0.5 divided by epsilon cubed. So this is all quite good. Still possibly room for improvement, but this is the best bound that's currently known, and it stood for over 5 years. Okay, so that's the story on adaptive data analysis. But now, remember, you can go over to the second quest version of the problem, which is the quantum version of the problem, which is the problem known as shadow tomography. So let me now tell you about quantum shadow tomography. So first let me tell you a warm-up for quantum shadow tomography before we get to the real problem. So the warm-up is kind of like the original data analysis problem we talked about, but in the quantum case. So here in this warm-up, you have a d-dimensional quantum mixed state row. So you can think of this as like a quantum source of randomness with d dimensions or d outcomes rather than a classical source of randomness. It's the state of some particles, maybe log d qubits. And again, you, the learner, are interested in some observable A. An observable is, well, it's actually a matrix, but it's the analog of a random variable in quantum probability. And let's assume that A is just a 2-outcome measurement. So really we have A and complement of A, which is the identity matrix minus A. And physically what this means is simply that you have some kind of measuring device with 2 labels on it, A and A bar. And when you put a quantum state, your particles, into this device, the measurement outcome is either A or not A. And you learn whether A occurs. And the particles, when they come out, they're in some collapsed state, rho prime. So measuring affects the state. And I'm going to write, this is non-standard rotation, but I'm going to write rho of A for simply the probability that your measurement outcome will be A if you measure the particles in state rho. Okay, so mathematically, this is the trace of rho times A. But you can just think of it as like the probability of measuring A, or getting a measurement outcome A when you measure particles in state rho. And in this warm-up, you want to estimate this quantity to within plus or minus some tolerance epsilon for this observable or measurement A that you know. And again, you can pay for many copies of your quantum probability source, many copies of your state. So you can pay to get n copies of your particles whose state is rho tensor power n. And then with these, you can do whatever you want, but you have to estimate this rho of A probability. So what should you do? Well, in fact, the solution to this problem is exactly the same as the solution to the classical problem. And you can, in fact, use the classical polling theorem again. You just take your n copies of rho and you pass them each through the measuring device, and you either get A or not A, and you output the empirical fraction of the times that the measuring device pointed to A, that you got the outcome A, divided by n. And basically, by definition, says the right expectation. And the same classical polling theorem tells you that your estimate will be within plus or minus epsilon, except with probability delta, if you let n be the same amount, log 1 over delta over epsilon squared. And again, there's no dependence on d, the dimension of rho, at all. Okay, so that's fine. And now let's move into the actual shadow tomography problem, not the warm-up. And I'll first tell you the original non-adaptive case of this problem, which was introduced by Aronson in 2017. So just like in the classical case, the situation here is that you have a learner that's interested in multiple observables or two outcome measurements, A1 through AM, and you want to simultaneously estimate all of their probabilities, rho of AT, up to some plus or minus epsilon for all 1 through M, A1 through AM. And again, you can pay for n copies of rho, and then you can do whatever you want with these copies, but at the end you have to output m estimates for all these probabilities, and you want them all to be epsilon accurate. So what can you do? Well, here there's a difficulty. In the classical case, this was easy. We just took our n samples, like in the classical polling theorem, and reused them to estimate all of A1 through AM, and we got the result we wanted with around log m over epsilon squared samples. But here in the classical case, there's no real notion of reusing samples. There isn't even exactly a notion of samples per se. That means you kind of can't easily sort of simultaneously estimate, do all these empirical estimates. Maybe the only thing you could do is maybe try to do them sequentially. But even this will have some difficulties, because when you, let's say, pass your state through the A1 measuring device n times in effort to measure rho of AT, the probability of AT under rho, well, even this disturbs the state. When you measure a quantum state, it gets affected. And so therefore, like, even if you were doing this sequential idea and tried to measure the second one with the same n particles, you wouldn't necessarily be getting the right answer. But this has exactly the same flavor as the difficulty in adaptive data analysis. Somehow you've disturbed the state of your probability, the state of your system, by making your measurement. Okay, and this was observed by, oops. Oh, I'm getting my slides all wrong. This was observed in a subsequent paper about shadow tomography by Aronson and Rothblum in 2019. They made this connection. They made a connection more with differential privacy, but I think the right analogy is to adaptive data analysis. Okay, so actually, given that in the shadow tomography problem, you're going to have to face some of the same difficulties you faced in adaptive data analysis, you may as well also study the adaptive case and the quantum case. If you're going to have to overcome these difficulties anyways, why not just even fight against the adaptive case in the quantum case, you might imagine. So this is really the problem we're going to end up studying, the adaptive version of shadow tomography. And here you have to pay for n copies of your quantum state rho up front. And then an adversary presents to you two outcome measurements, or observables A1 through AM sequentially. And after you get the teeth one, you have to do something with your state and then output an estimate of the probability of AT under rho up to some plus or minus epsilon. And the adversary can act adaptively. It can choose what a t+1 to feed you based on everything that happened in the past, A1 through AT, and even on rho. And you want that all your estimates, all M estimates, are correct up to plus or minus epsilon with high probability. So this is the adaptive shadow tomography problem that we'll discuss in the rest of this talk. So again, let's go to the board and find out what the records are for shadow tomography. Okay, so as I mentioned, this problem was introduced by Aronson a little over 3 years ago. And he solved it and showed happily again that you can solve this problem using a number of samples or copies, which is polylog in M, polylog in D, and polynomial in 1 over epsilon. And this is great. It shows that similar to adaptive data analysis, you can get the desired result with roughly the right dependency on all the parameters, or at least good dependencies on all the parameters. And he actually only solved the non-adaptive case. By the way, it's quite important, you might imagine practically, to have a logarithmic dependence on the dimension d, because log of d is really the number of qubits in the state row. Okay, so we really don't want to have a dependence on d here. We'd rather have polylog d. Okay, so shortly thereafter, in a work of Aronson, Chen, Hazan, Kale, and Nyack, they brought in some actual sort of classical learning theory ideas and got a slightly improved result. Same dependency on log m and log d, but they got the dependence on epsilon down to 1 over epsilon to the 4th. That was also non-adaptive, which is a modest improvement, but like the idea introduced in that paper is very important, and we'll use it in our work. Then later we come to this 2019 paper by Aronson and Rothblum, which made the connection to adaptive data analysis and differential privacy. And using this, they made a big improvement on the log m term. They got it down to log m squared. And the log d term got worse, and the epsilon term got worse. But I still rank it number 2 because, as I said, log m is the most important parameter to me. And that also handled the adaptive case, which is nice. Okay, and so what I want to tell you about today is this recent work I had with Costin Badescu from a few months ago, where we solved the problem with, again, log m squared, dependency on m, the number of observables, and log d to the 1 and epsilon to the 4th. Okay, and so it matches all the best exponents for all 3 parameters and simultaneously achieves all of them. Great, so let me tell you about our route for how we achieved this solution. And it kind of comes with 3 main stages. So in the first one, we show how shadow tomography reduces to a simpler problem that you might call quantum threshold search. And this loses a factor of log d over epsilon squared. And this reduction is via mistake-bounded online learning. And I should say that we show it because, in fact, this part was already known. The second part of the route is to show that threshold search can be done with log squared m over epsilon squared copies of your quantum state by further reduction to a problem called, or that we call, stable threshold decision. And you see by multiplying these 2 quantities together, log squared m over epsilon squared and log d over epsilon squared, we get the log m squared times log d over epsilon to the 4th number of copies in our final bound. Okay, and the final split, number 3, is to show how to do this stable threshold decision problem with a number of copies that's log squared 1 over delta, and I'll explain what this means, but delta has to be like 1 over m, so this is how these 2 results connect, over epsilon squared copies. Okay, so those are the splits, that's how we split it up. And let me make some comments on each of these. So as I said before, this first piece was already known. We didn't really do anything here except like fill in a few minor details that were not written down. This is the paper by Aronson, Chen, Hazan, Kale, and Nyack. This third segment, it's actually kind of in the Aronson-Rothblum paper. If you look very carefully, it's not, they didn't phrase it quite like this, and it's a little bit hard to find. It's somewhere on, page 47 or something, but it's kind of in their paper already. And I suppose this second split is the most novel part, showing how to do threshold search with log squared m copies. But it's even conceivable that, like, Aronson and Rothblum could have gotten this result if you just sort of asked them to, based on this third split. So you might say, like, it kind of seems like all these pieces were sort of already in previous papers. So what was your contribution? I mean, I think our contribution was to really kind of clarify this route and optimize these second and third strategies and do them more cleanly. So in the Aronson-Rothblum paper, like part 2 and part 3 here were all kind of mixed together, and it wasn't exactly clear. One couldn't easily exactly extract the statements of these results from them. So by kind of clarifying these, separating them out, and doing them a little bit more cleanly, we were able to get these improved parameters. Okay, so now I want to tell you about each of these pieces of the route to our result, and I'll start with this first one, even though I'm just going to explain the work in another paper, this Aronson Chen Hazan Kale Nayak paper, because it'll be interesting to see all three pieces of the route. So the first thing I want to talk about is how shadow tomography reduces to a simpler problem called, or that we call quantum threshold search, via mistake-bounded online learning. So here's what you should imagine. You're kind of wanting to do quantum tomography. You kind of want to learn the probabilities of various ATs under the unknown state row. But for this, you should imagine you're an absolutely clueless student and you don't know anything at all about the state row. You don't have access to any copies of row. You have no information. But there's still this person grilling you, asking you to estimate the trace row AT, like the probability value of AT under row. So you're going to make some mistakes because, you have to start out by making guesses. But in the setup of mistake-bounded learning, you imagine that there's a third character, a teacher, who will fix your mistakes for you, who will explain to you what mistakes you've made. And what this paper shows, using techniques from online convex optimization, is that there's a strategy for the student to do this, to get accurate guesses of the probability value of all these ATs, all m of them, such that the student never makes more than order of log d over epsilon squared mistakes. And this is independent of m. Okay, and you perhaps have even seen this result in the classical learning scenario. And this paper extends it to the quantum version, so it's a generalization where vectors become matrices. So let me just explain the scenario a little bit more. So here is the clueless student, and they have no idea about what's going on with this state row, but they're being asked to estimate these row of AT values. But as we mentioned, they have a teacher, and she actually does know some things about the state row. She, you should imagine, has some information about row. And the third character is the adversary, and this adversary is going to try to grill the student on these expectation values, row of AT. So the game goes something like this. So first the adversary says, okay, what is row of A1? What's the probability of getting outcome A1 if you measure my unknown state row? And the student doesn't even know row, so they're like, they have to guess, I don't know, 0.7 plus or minus epsilon? And just for this story, let's imagine the teacher is like, oh, actually, by an extremely lucky guess, that's actually correct. In which case the teacher doesn't say anything. Well, you can imagine the teacher says pass, like you passed that round. Okay, so then the adversary continues the grilling and says, what's row of A2? And the student, they don't know very much at all, so they do know that row of A1 is around 0.7, so that's good, but they still more or less are going to be guessing here. So let's say maybe 0.24 as a guess, plus or minus epsilon. And now we should imagine that this is actually wrong. And so when that's wrong, the teacher will say mistake, and the teacher will provide a correct value up to maybe some better tolerance, epsilon over 2. So the teacher might say, well, it's actually 0.45 plus or minus epsilon over 2. And the student says, okay. And then the adversary continues and says, what's row of A3? And this game goes on for a while. And as long as the student gives accurate responses, the teacher will pass them. And when the student makes an inaccurate guess, the teacher will correct the student. So this will go on for several chapters. And let me clarify a little bit about the properties of the teacher we're assuming. So we're going to assume that if the student's estimate really is correct within epsilon, the teacher will always say pass. We'll also assume that if the student's estimate is wrong by 2 epsilon or more, the teacher will definitely say mistake, call them on the mistake there. But we'll imagine there's like a little bit of a grace area, a gray area, where if the student's estimate is correct within between epsilon or 2 epsilon, then the teacher might just allow them to pass, or the teacher might declare a mistake. That's up to the teacher, and it won't matter. And finally, we'll assume that when the teacher corrects the student, the corrections are always a little bit better. They have tolerance epsilon over 2. Okay, so this is the scenario we imagine for the teacher. And now the result of Aronson, Chen, Hazan, Kale, and Nayak says that there is a strategy for the student, a strategy the student could implement such that they never make more than order log d over epsilon squared mistakes, no matter how long the game goes on for. As long as this teacher property holds, the student can achieve this small number of mistakes that doesn't depend on m. Okay, so that's great, but we're talking about shadow tomography. And so you see what we need for shadow tomography is for the student to implement the teacher. So in the shadow tomography problem, you actually have access to rho as the learner, and you can implement this student strategy, which is good, so that you'll never make any more future mistakes about your estimates. But in order to do that, you need to have the teacher correcting you. So really, the shadow tomography algorithm has to somehow implement the teacher properties. And if it can do that, then it can also run the student strategy and thereby ultimately give correct estimates for all of the a sub t's. And what I want to say here is what the teacher's job is to really solve this problem that we're going to call adaptive threshold search. So let me clarify that a bit more. So let's think about what the teacher really has to do. And this takes us to the second part of the strategy. So we've seen this first part, reducing shadow tomography to adaptive threshold search. And we'll talk about that adaptive threshold search now. Okay, so let's just think about what the teacher has to do, not for all time, but from the beginning of the game up until the first time that the teacher declares a mistake. So let's think about that initial portion of the game. So the teacher is going to pay for some number of copies of rho. Well, really, the teacher is the shadow tomography algorithm now. So they're going to pay for some number of copies of rho. And what we want to show, or what actually our paper does show, is that will be sufficient for the teacher to pay for this many copies of rho, log m squared over epsilon squared copies of rho. And then the teacher, from the teacher point of view, they're presented with a sequence of pairs, observable pairs, AI, and guess pairs, theta I. The guess values are coming from the student algorithm, and the AIs are coming from the adversary. And there's going to be at most m of them. And this is the teacher properties right here. Given observable AT and a guess theta t, the teacher is supposed to say pass if the true value of the observable under the state rho A of t, is within epsilon of theta t, the guess. And the teacher must say halt. We had the teacher saying mistake before, but since we're imagining sort of stopping the game when the first mistake is found, I'm going to change that word to halt. So the teacher has to say halt if the expectation value is not within 2 epsilon of the guess. And remember, in the gray area where theta t is between epsilon and 2 epsilon away from rho of AT, then the teacher can say either pass or halt. It's fine. And there's one more teacher property. The teacher property is that when the teacher declares a mistake or declares halt, they have to supply the student with a correct estimate, or an estimate that's correct up to some plus or minus epsilon over 2. But actually, that part is easy. Since the teacher is going to be spending this many copies of rho, or purchasing this many copies of rho anyways, this is much bigger than 1 over epsilon squared. You can just have the teacher like buy an extra additive about 1 over epsilon squared copies of rho as a holdout. And when it finally does declare halt or mistake, it can separately on the side use these fresh copies to get an accurate, like epsilon over 2 accurate estimate of the true expectation value that it can provide back to the student. So this part is cheap, and the only thing we really have to worry about for the teacher is solving this problem. You know, saying pass if the student's guess is close to the correct value, and saying halt if the student's guess is far from the correct value. Okay, and then if the teacher can solve this problem, then they just have to do this over and over for each mistake. So if they're going to use log squared m over epsilon squared copies of rho for each mistake, and the student algorithm is only going to make log d over epsilon squared mistakes. As I said before, that's where you multiply these together and get log squared m log d over epsilon to the 4th. Okay, so the teacher's task here is like a little bit complicated, but we can make it a bit simpler. So here, the teacher's task involves two-sided inequalities, but there's a simple reduction from two-sided inequalities to one-sided inequalities. I put it there on the slide. You can take a look at it. But basically, if the teacher can solve the one-sided version of this problem, it's easy to do the two-sided version as well. So we can make the teacher's task look a little bit more simple like this. So there's now like a threshold, theta of t, and the teacher should say pass if the expectation value is more than epsilon below this threshold, and the teacher should say halt if the expectation value is more than epsilon above this threshold. Okay, so the expectation is kind of that the expectation that theta t will always be an upper bound on the true expectation value, and you have to catch the student in a lie if that's not the case. Okay, good. So and that's why it's called threshold search, by the way. We have a threshold problem. We're searching for the first time when we have a mistake, and hence the name. And in fact, even this is a little bit complicated. It's also quite easy to show a little reduction that says at the expense of a multiplicative factor of 1 over epsilon squared in the number of copies, you can reduce the case where the teacher only has to handle when all the thresholds theta are a half, just some arbitrary fixed number half, and all the epsilons are also a constant, let's say 1/4. Okay, if you can handle this case, then there's a very simple little reduction based on just the classical Poland theorem itself applied to each observable that lets you handle the general case. Okay, so the upshot of all of this is we can even get rid of this epsilon squared factor building it into the previous reduction, and finally say that the adaptive threshold search problem, or rather, in fact, our solution to the adaptive threshold search problem solves this task. The learner's gonna, there's some state row, the learner's gonna pay for order of log m squared copies of it, and then it's gonna be presented with a sequence of observables, A1, A2, etc., at most m of them. And when the learner is presented with AT, they have to say pass if the probability of AT under row is less than 1/4. They have to say halt, and the game stops if the expectation value is bigger than 3/4. And if it's between 1/4 and 3/4, they can say either, and the game continues if they say pass, and the game stops if they say halt. Now, if you look back at the actually original shadow tomography paper by Aronson in 2017, he actually did it by, a key component in that was solving exactly this problem. And it was in the non-adaptive case rather than the adaptive case, where you're given all the A1 through AM up front. But anyway, he solved it, and he solved it with n, the number of copies, being proportional to log m to the 4th. Okay, so getting this down to log squared m, and also making it adaptive, is in some sense our most important contribution. Okay, so let's think about this adaptive threshold problem some more. Pay for a bunch of copies of row, you're presented with A1 through AM in sequence, and sort of the idea is you're kind of expecting their probabilities to all be at most 1/4. You want to pass whenever you think that's the case, and you want to halt if you ever discover one that's got a big expectation value, at least 3/4. So how are you going to do this? So let me tell you a natural idea, which is like the basic non-working idea that we kind of, in some sense, discussed already. So the first thing you might try would be this. You would say, okay, I'm going to try to let n be a large constant times log m. We can't get that. We can only get log squared m, but we could imagine trying to get order log m samples. And for each observable, AT, as it comes in, I'm just going to estimate the probability value in the naive way. I'll just pass it through the I'll pass row through the measuring device n times, and I'll just try to detect if the probability row of AT is bigger or smaller than a half, okay, where a half is just some number that's in the middle between 1/4 and 3/4 here. And if I do that, then I'll correctly decide whether it's at most 1/4 or at least 3/4, except with probability 1/20m. Okay, that's what the classical polling theorem would tell us. We are using a constant value of epsilon here. So this works for the very first observable, A1. It's fine, but as we've mentioned before, maybe you use all your n samples to estimate row of A1. It seems to be less than a half, so you pass. But then conditional on passing A1, the state of your samples, or you don't have samples, the state of your particles, row tensor n, is disturbed. When you measure quantum states, it affects the state itself. Okay, and so then when you move on to A2, it's not clear what to do. Now, let's talk about some idea in the direction of improving this. So let's imagine that row A1 really is smaller than 1/4. Okay, so it's let's call that a must pass observable, because you have to say pass to it. Well, 1/4 is quite far from a half, which is the threshold you're actually using. So the probability that, if you just use, classical sampling, the probability your estimate would be bigger than a half is exponentially small in the number of samples you use. So if you were using like 100 log m samples, then the probability of you wrongly halting here is really, really small. You can make it like 1/m to the 10. And bear in mind that there are only m observables at all. So this looks pretty good, especially when it's combined with this other fact here that I've put up, the gentle measurement fact. So the gentle measurement fact is like a phenomenon that's very important and basic in quantum information processing. And it says the following: if you have any state, and I wrote it as curly row because we're actually imagining applying it to n copies of the real state row. So if you do any 2 outcome measurement on, like our estimate here, on curly row, and the probability of outcome B occurring is really small, then if you do that a measurement and not B occurs, which is the expected outcome, then the disturbance caused by the measurement is really small. More specifically, the trace distance, which is some natural measure of how similar two quantum states is. The trace distance between rho and rho conditioned on the expected measurement outcome, not B, is at most square root delta, where this is square root of the probability. Okay, so again, if you're doing a measurement and one of the outcomes is very unlikely, and you do the measurement and you get the likely outcome, then in that circumstance, the state does not change very much. It's not disturbed by very much, and the disturbance is like the square root of the probability. Okay, so if we apply that to this idea, we see that if you have a must pass AT whose true expectation is less than 1/4, and you can imagine here B is like the outcome that you do, you measure it n times, and your empirical estimate tells you it's bigger than a half. That's very unlikely. The probability of that is less than, let's say, 1/m to the 10th. So when you do the measurement and you see that the likely outcome, that your estimate is that it's less than a half, then you've disturbed your state only by a very small amount, the square root of 1/m to the 10th, which is like 1/m to the 5th. And that's intuitively very good, because like 1/m to the 5th is really small. So I'm about to like cheat a little bit, but what I'm telling you here is the correct gist of the analysis. You see here that like for these must pass ATs, whose row of AT is less than 1/4, you'll basically never accidentally halt on them. And because the probability of accidentally halting on them, if you're truly using rho to the n copies of rho, would be like 1/m to the 10th. But furthermore, when you do successfully pass them, you disturb your state only like 1/m to the 5th. So you can kind of union bound over that. There are only m observables, and say that all of these disturbances are still like very negligible. And therefore, you'll kind of like never in the whole course of the threshold search like accidentally halt on a must pass AT. And furthermore, conversely, if you're given an AT whose expectation value is under rho is bigger than 3/4, so you must halt. I mean, remember your test is you're going to empirically estimate whether the expectation value seems to be bigger than a half. That's if you're truly using n copies of rho, fresh copies of rho, the chance of getting that answer wrong would again be exponentially small in m. As long as you haven't disturbed your n copies of rho too much as you're going along, then that will still hold. So you see, like the must pass ATs don't really give you any trouble. They won't disturb this idea much, this idea of reusing the state each time. And the must halt ATs also should be fine. The trouble is, and the thing that makes this really difficult, is like the gray area ATs. Observables AT whose expectation value is really close to the threshold of a half that you're looking at. And let me try to illustrate why those are a problem. So let's say you're going along, maybe you've passed on a bunch of observables and they're all must passes. You don't know that, but let's say they were, so that you haven't disturbed the state very much. And then you're given, the adversary gives you an AT whose true expectation value is, let's say, a teeny bit less than a half. And maybe this tiny amount less than a half is cooked up so that the probability that you would estimate wrongly that the expectation value is bigger than a half is very small, but not ridiculously small. So let's say like 1 over 10,000. Okay, so actually, you don't mind passing this AT. You don't mind halting this AT. It's on this AT. It's in the gray area. So you don't really care what you do. You don't mind halting on it, but you probably won't, right? I mean, the probability that you'll halt on it is only 1 in 10,000. So you'll probably pass it. But there is a worry here because this gentle measurement fact tells you that, after you, let's say, pass it, or rather assuming you pass it, the disturbance to your state, your n copies of rho, might be as large as the square root of this. Okay, and the square root of this is 0.01, like 1%. So you've kind of disturbed the state kind of a lot. And indeed, the real trouble comes now if you imagine that the adversary gives you 100 such ATs in a row. And this is worrisome. Oh, let me say a little bit why this is worrisome. This is worrisome because, you'll probably pass on all of them, which is fine. But, with 100 disturbances in a row, each of magnitude 0.01, then you could get into a situation where, the total disturbance to your state is like 1, like you've completely ruined it. And now everything that you do subsequently might not work. So that's rough. But we got to fix it. And in order to fix that, there's a certain dream that you might have. And let me explain what this dream is that could assist with this difficulty. So imagine there was some way to measure your n copies of rho so as to accept or reject according to whether the rho of AT is bigger than a half or not, while still somehow ensuring that the disturbance to your n copies of rho is small compared to the probability of accepting, which is like the probability of halting. So maybe like smaller by a factor of 10. Well, as with dreams, you might think this is quite inconsistent with all the laws of probabilities. That's how a dream goes sometimes. But because, the gentle measurement tells us that this could be as large as the square root of the probability of acceptance, which is much bigger. So how are we going to get it to be at most 1/10 the probability of acceptance? Well, let's see. So let me just rearrange this. This is like equivalent to saying that the probability of accepting should be 10 times bigger than the disturbance. And why, if we could achieve this dream, would it be good? The punchline is, suppose we somehow could achieve this dream, then as you process A1, A2, A3, and A4, your main worry is this the gray area ATs, which have this property that they really could add a lot of disturbance to your state, and you don't mind halting on the gray area ATs because their expectation value is bigger than a quarter. So you kind of even want to halt on these gray area ATs. And this dream kind of tells you that the cumulative probability of you halting on, the gray area ATs is always more than 10 times the disturbance. So you can somehow never get into trouble because whenever the amount by which your state has been disturbed gets large, the cumulative probability of you having halted on one of these gray area ATs is like even larger. So you kind of never get into a situation where you need to worry because you can never get the disturbance to be really high without already having found an AT whose expectation value, rho AT, is bigger than a quarter. So, I mean, this is where some of the details are being hid from you, but this is basically the idea. Okay, so this brings us sort of the third part of the algorithm, what we may call the stable threshold decision problem. So again, we call it that because you want to make this threshold decision about whether rho's expectation value is sort of bigger or smaller than a half, and you're willing to make that bigger or smaller than a half with some tolerance that's like up to a quarter even. But you want this decision to be done in a stable way, such that the disturbance to your state is small, even compared to the probability of you accepting. Okay, which brings us to the final split of our route, which is this solving this stable threshold decision problem with a number of copies, which is log squared 1 over delta, where delta is a parameter I haven't explained yet, but I will in a moment. Okay, so let me tell you our stable threshold decision result at a high level. So here, a learner is going to pay for log squared 1 over delta copies of rho. And the learner has some particular observable A that it knows, and it wants to accept or reject the statement that rho of A, probability of A under rho, is bigger than the fixed amount 1/2. And you're willing to tolerate an inexact check. Okay, what I mean by this is, I'll come back to that in a second, but let's say an exact check or an exact-ish check is if you don't exactly check whether rho A is bigger than a half or not. Maybe you check rho A bigger than 0.499 or rho A bigger than 0.501. Those are all okay. These exact-ish checks are okay. What we do want, though, is that maybe you won't precisely check rho A greater than or equal to half. You might check something kind of vaguely in the neighborhood. But you shouldn't be doing a really wildly inaccurate check, except with probability at most delta. Okay, we're willing to tolerate an occasional really wildly wrong kind of check. And we're going to set delta to be like 1 over 20m, where m is the total number of observables we have to handle. And then again, we can do this union bound thing where there's only m observables. We make delta this small. The probability we ever get any kind of grossly inexact check is very small. And so we don't have to worry about that. And that's how we go from this log squared 1 over delta to log squared m sample complexity or copy complexity. Okay, so the goal in this stable threshold decision problem is, as we sort of suggested before, we want to solve this problem, but we want it to be the case that the distance, or disturbance between n, independent copies of rho, and these n independent copies of rho conditioned on rejecting, or passing as we used to call it, is small even compared to the probability of accepting. Okay, so better than the square root relationship that comes from gentle measurement. So as we said, the most naive thing is to just do classical polling. Just take your n copies and measure A n times and see if you got more or fewer than half outcomes of A. But this has too much disturbance, too much damage to our state. So what is the idea for this? And this is the idea that comes from differential privacy, is to artificially inject noise into the measurement. Okay, and this is actually where the sort of exact-ish checks come from. So the naive thing to do would just be, measure A n times and accept if the number of times you got the outcome of A rather than not A is at least half n. So instead of that, what we're going to do is a similar thing, except we'll take the number of A outcomes and add this noise x, which has a distribution independently of an exponential random variable with mean something like 20 times root n. Okay, and then we'll throw this noise in and make our decision based on that. And you can see that, well, first of all, as long as the random variable x, the amount of noise, is kind of similar to its mean, then we will be getting a pretty exact-ish check. In fact, the probability an exponential random variable is, you see, the only case in which we'd be really worried about this exactness of our check is if somehow the random variable x were bigger than, let's say, 0.001n. That would make it for a really inexact check. But 0.001n is like a number of standard deviations, which is like proportional to root n. And the probability an exponential random variable is like more than its mean by root n standard deviations is like exponential in minus root n. So you see, if we take n to be log squared 1 over delta, then exponential in minus the square root of this will be smaller than delta. Okay, so this is where the log squared 1 over delta dependence comes in. And the idea is that by putting this noise in, you're not putting so much weight onto the actual outcomes of A. You're kind of making your decision partially based on noise. And because of that, you might hope that you haven't somehow disturbed the state too much. And in fact, proving, this is the actual algorithm, I suppose, and proving this works is actually pretty much a 100% classical theorem. Even though it's talking about quantum states and observables, when it comes down to proving this, you're basically proving a classical probability theorem. And indeed, it comes down to proving literally this theorem that I've put up here on the slides. So I won't read it out loud, but you can pause and look at it if you want. And I just think this is like a nice theorem, kind of a differential privacy type theorem that we worked out. And what is the proof of this theorem? Well, math. I mean, it's a theorem that's entirely elementary probability. And well, here again, you can pause if you like and read this whole proof. But that's the whole proof. It's just some elementary probability calculations. Okay. I should mention also that, as I kind of alluded to before, if you squint at the Aronson-Rothblum paper, you can extract from it a theorem that's pretty much the same as this. It's a little bit weaker in a few ways, but actually the ways in which it's weaker don't affect how it gets used. And so you can even extract the result you need if you work hard from the Aronson-Rothblum paper. But I think the way we stated it and proved it is a lot more clean and easy to understand. Okay, so that's the summary of our whole route to achieving adaptive shadow tomography with improved sample complexity that has the best known exponent on log m and log d and on epsilon. Now, I want to talk just at the end of this talk here about this exponent on log m, because as I said, I feel log m is the most important parameter, and our exponent here is 2, and I'd really like to get this exponent down to 1. So grinding for the sub 2 exponent on log m is my real dream here, and let me explain why. So our paper shows that another problem, that's the second quest version of hypothesis selection, namely quantum hypothesis selection, reduces the problem of shadow tomography. So if you could do shadow tomography with a log m dependence on n, you could actually do full state quantum tomography with a quadratic dependence on d. And this would be a great result because although this is known, the methods known to do it use a lot of heavy group representation theory. And it would be really cool if you could just achieve full state quantum tomography with optimal d-squared copy complexity by reduction to shadow tomography. So we have a stream of attempts at achieving this, and I hope you follow us and stay tuned, and hopefully we'll get that sub 2 exponent on log m soon. So thanks for watching, and I'll see you next time.